The race between the USA and China in customized cloud CPUs, the geopolitics of AI infrastructure. Aloha, my name is Chung-Ho Alex Yu, and I am a professor of data science and artificial intelligence in Hawaii. In this presentation, I will discuss the race between the USA and China in customized central processing units for cloud computing. To meet the unprecedented performance, efficiency, and scalability demands of artificial intelligence, the world's largest cloud providers are no longer relying solely on off-the-shelf processors. Hyperscalers have discovered that commodity x86 chips, while versatile, are insufficiently optimized for the specialized workloads and enormous data flows in modern data centers. As a result, companies like Amazon Web Services, AWS, Google Cloud, and Microsoft Azure have taken the bold step of designing their own chips. These purpose-built processors allow them to fine-tune compute, memory, and I/O subsystems to their own unique workload profiles, thereby achieving superior performance per watt, lowering costs at scale, and ensuring a tighter integration between hardware and software. A key shift behind this trend is the move from Intel's x86 architecture to ARM-based designs. The difference can be understood through a simple metaphor. Imagine two types of toolkits. The x86 architecture, CIS, complex instruction set computing, is like a giant Swiss Army knife with dozens of blades and gadgets. It can do everything, but the complexity makes it bulky and harder to optimize for speed and efficiency. In contrast, the ARM architecture, RISC, reduced instruction set computing, is like a streamlined toolbox containing only the most commonly used tools. Each tool is simpler, but because of that simplicity, tasks can be executed faster with less energy wasted. In cloud data centers, where millions of similar tasks are repeated billions of times per second, ARM's minimalist approach often delivers better efficiency and performance per watt. This explains why hyperscalers are embracing ARM as the foundation for their custom CPUs. AWS's Graviton family represents the most mature of these in-house CPUs. Based on ARM's Neoverse architecture and designed by AWS's Annapurna Labs, Graviton chips are already in their fourth generation and power a wide swath of EC2 instances. Google has introduced Axion, its first custom ARM-based CPU, which pairs with its titanium offload system to free up processing cycles for customer workloads. Microsoft unveiled Cobalt 100, also ARM-based, which integrates into Azure's virtual machines and complements its in-house Maya AI accelerators. Despite being competitors, all three American hyperscalers converge on a critical supply chain fact. Their processors are fabricated by Taiwan's Semiconductor Manufacturing Company, TSMC, on cutting-edge 5-nanometer or smaller nodes. Neither Intel nor Samsung has been chosen for these high-volume cloud CPUs. Intel Foundry is still struggling to regain process leadership, while Samsung's Foundry, although advanced in some areas, has faced yield and reliability concerns. TSMC remains the clear leader in delivering both the density and power efficiency required at hyperscale. China's cloud providers have followed the same strategic logic, but with a crucial limitation. Alibaba has developed the Yitian 710 CPU, ARM v9, 128 cores, while Huawei has produced the Kunpeng series for general compute and the Ascend series for AI workloads. Tencent has built the Zixiao Inference Accelerator to support recommendation engines and advertising, and Baidu has introduced the Kunlun AI chip for training and inference. On paper, these designs are impressive, comparable in architectural ambition to their US counterparts. Yet they face a structural bottleneck. Due to US export controls, they cannot be manufactured at TSMC or Samsung on advanced nodes. Instead, Chinese firms rely on Semiconductor Manufacturing International Corporation, SMIC, China's leading foundry, which is currently limited to 7-nanometer class production through older lithography methods. This puts them at least 2 generations behind the cutting edge. The performance gap is tangible. AWS Graviton 3, built on TSMC's 5-nanometer process, demonstrates up to 30% better compute performance and 50% higher memory bandwidth compared to earlier iterations, while consuming less power. Google and Microsoft make similar claims for their Axion and Cobalt chips, highlighting superior energy efficiency and throughput relative to x86 alternatives. By contrast, Huawei's Kunpeng CPUs and Ascend accelerators, constrained to 7 nanometer or larger nodes, operate with higher power draw and lower transistor density. This limits the scale of cores, cache, and interconnect bandwidth they can deliver. In AI inference, where efficiency and latency are paramount, these disadvantages become even more pronounced, forcing Chinese providers to lean heavily on software optimizations such as quantization and model compression. In conclusion, US hyperscalers enjoy a dual advantage. They lead in chip design maturity and also enjoy manufacturing access to TSMC's most advanced process nodes. This combination allows AWS, Google Cloud, and Microsoft Azure to roll out increasingly efficient, powerful, and cost-competitive infrastructure, reinforcing their dominance in the global market for AI and cloud computing. However, this lead is not without vulnerabilities. American hyperscalers are almost entirely dependent on TSMC for fabrication, meaning that any geopolitical disruption in the Taiwan Strait could threaten the backbone of global cloud and AI infrastructure. Moreover, as China invests heavily in semiconductor self-sufficiency, its cloud firms may gradually close the gap through architectural innovation and domestic demand. Thus, while the US providers currently enjoy structural advantages, the global race for cloud silicon remains not only a contest of technology, but also a contest shaped by geopolitics, supply chain resilience, and the evolving balance between design and manufacturing ecosystems. So, what do you think? I'd love to hear your thoughts. Please drop your comments here. If you found this presentation informative, please like, share, and subscribe. Thank you for watching. Mahalo.